you? How's it going?
Oh, thank you. I'm fine. I'm happy I found my way here to the Sci-Mic stage. I have brought my compass that showed me the way how to go here, and it just worked out well.
I know. I'm surprised you can even read a compass. I can't even read a compass. I have no idea. I'm just kidding. But yeah, so Dr. Roland Winkler is an awardee for the science breakthrough on magnetism. He found a new type of magnetism. Before we get into that, why magnets? What's so interesting about magnets?
First of all, let me get this straight. I'm, so to say, not the one who brought up this new type of magnetism, but I have been myself engaged in a related research, and so to say, along the way, I also rediscovered or discovered myself in my own work what now we are, so to say, looking at here as a new type of magnetism that is emerging.
Awesome, awesome. Great. Yeah. Do you want to explain to us just kind of like a refresher on like what's so interesting about magnets? What are magnets?
I mean, magnets I've just brought here, a few, are certainly a nice toy to begin with. We know this basic property of magnets that, they do have a north and a south pole, and when we bring north and south together, they do attract each other, and if we try to do it the other way around, it just doesn't work. They repel each other. But this is, so to say, what is long known as, in physics, we call ferromagnets, which we can visualize, so to say, as multiple magnets being aligned in parallel. When we take two of them next to each other, this becomes like twice as big a magnet. But nature has given us a second form of magnetism, which we call anti-ferromagnets, because essentially it means that we have magnets anti-parallel to each other, so that they cancel out, roughly speaking, when we look at them from some distance. When I bring these two magnets next to my compass needle, it will by far less respond to them as if I just bring one of them. And this second form of magnetism, anti-ferromagnetism, has been known by now for about 100 years. And most recently, it has been discovered that there is essentially a third form of magnetism, which is kind of halfway in between the ferromagnetism of a magnet like this one and the anti-ferromagnetism of two magnets or multiple magnets anti-parallel to each other.
Does this third form of magnetism have different properties compared to like the ferromagnet and the anti?
It has, so to say, properties that are halfway in between what we associate with a ferromagnet and the anti-ferromagnet.
Well, are you trying to kind of like take advantage of these properties, or are you just looking into what can we even do with this third type of magnetism?
Right now, it is certainly, we are still in an early stage, so to say, of exploring what the different properties are, how they can be useful. So with ferromagnetism, this has been exploited in a number of ways. So famous example, so to say, that many of us carry around nowadays are the hard disk drives that are built into our computers, which essentially use ferromagnetism to store information. And more recently there have been attempts to also exploit the different properties of antiferromagnets compared to ferromagnets, but in a way it becomes more difficult to exploit these properties because they respond, so to say, by far less to the environment than a single ferromagnet does. And in that sense, magnets, as they are called, these new type of magnets, being halfway in between, may open more opportunities than the antiferromagnets that have been known for 100 years, but say for a long time have been more regarded as a toy thing for physicists to play with than anything useful. And in that sense, having this new form of magnetism halfway in between where we know what to do with it and the other ones that are kind of cute but nobody really knows, that may open new avenues.
So if magnets have been around for like hundreds of years and we knew about like ferro and antiferro, but like how does one even lead to the discovery of a third magnetism? What led to that discovery?
That discovery was mostly inspired by theory that groups have been doing calculations, properties of magnetic systems, and realized that when they looked at certain types of material, they showed properties in the calculations that didn't match our ordinary understanding of ferromagnets nor our understanding of antiferromagnets. And then that's the point when you start scratching your head and look more carefully and work it out more systematically, and you find new things.
Yeah. For someone that just only interacts with magnets just like on my refrigerator or just to hold up a picture, I guess like what gets you excited to even study magnets in the first place?
Magnets are a fascinating playground because they ultimately do have a very rich variety of how magnetism can be realized in nature. So what we have been talking about so far in some way is just the most basic form of magnetism. We sometimes call this collinear magnets, where these magnets are parallel, anti-parallel to each other, but they can in nature also arrange in much more complicated ways. We can have here patterns in the plane of such microscopic arrangements of magnetic moments on the individual atoms in a complicated crystal structure, and it can even become three-dimensional, and that makes it a very rich playground with very diverse phenomena, and that's of course always fascinating to look at and play with.
Nice, amazing. All right, well, if you want to hear more about his science breakthrough, he will be presenting a talk. Are you presenting a talk tomorrow? Yeah, okay, at 11:30. Again, I don't know the room number, but I will open the door or the stage to some questions that we have. Yes. One moment, we're gonna get a microphone.
So, yeah, I'm a physicist, and I knew about ferromagnetism, but I do not know about what you're talking about at all. I'm just wondering, I'm wondering a lot of things, and I'll come to your talk and ask more questions, but I'll ask one now. What's the nature of the materials in which this magnetism is found? They're not ferrous materials, I assume, or are they?
I have somehow difficulties to understand your question.
Say it a little bit slower and louder.
Just a little louder, yeah.
The materials in which you see this semi-ferromagnetism, are they ferrous materials or are they some other material? What's the nature of the material itself?
The materials are all fallen into the class of magnetic materials. So previously, they had just been classified as antiferromagnets. So to say, antiferromagnets, from a certain perspective, is a large umbrella for different types of, we could say, any material that is not a proper ferromagnet previously has been classified as antiferromagnet. And in that sense, we have now been looking more carefully at the wide variety of antiferromagnetic materials and realized that we should really be more careful in our terminology because they can be very different in their properties.
I guess a follow-up with that, is there only, you know, we think of like iron as like one of the main like elements that are usually found in magnets. Has there been any look into what other types of elements in the periodic table that are leaning more towards these semi-ferrous magnets?
Typically, the alter magnets, the materials realized in this new type of magnetism are what we call compound materials. So iron is one of the elements from the periodic table, so there is only one type of atoms contributing to this crystal structure, whereas the alter magnets are realized by compound structures that typically have two different types of atoms built alternatingly into the crystal structure, and then realize in this new form of magnetism.
Amazing. Awesome. Well, thank you so much for joining me on the stage, and thank you for attending and hanging out with me at the Sci-Mic.